I am sure that if you have done a previous subject in statistics, that you'll be reasonably familiar with the idea of statistical regression. And this is the process of estimating the value of some variables based on knowledge of some other variables in a very crude sense. So when I've said estimating, sometimes estimation isn't necessarily the goal. Sometimes it's just explaining or understanding how variation in one variable is associated with variation in other variables. Now, a little bit of terminology here. We say that the ones that we're trying to explain we call dependent or response variables. And that's, I think, a fairly intuitive label. We say that those values depend on things we've measured or that they respond to them. And the opposite of that is either independent variables or sometimes predictor variables. So we use predictors to predict a response, or we use independent variables to predict the dependent variable. You'll also often hear this in terms of letters, because we'll often plot a graph of this, and if we do, we'll tend to, by convention, put the horizontal axis as labelled X, the vertical axis labelled Y, and we'll tend to put the predictors on the X-axis and the responses on the Y. So sometimes informally, although we should probably say these are the predictor variables and this is the response, you will often hear statisticians say, here are the X's and that's the Y. You may not have thought of this, but the word regression seems like an odd word because regression means sort of falling backwards or going backwards. It comes from the observations of Francis Galton, who, well, he was Charles Darwin's cousin actually, but he studied the heights of adults and the height of their parents. And what he saw was that, well, taller children, or taller children as adults, tended to have parents who were above average. But the interesting part was he didn't just observe that there was a connection between the heights of people and the heights of their children, but the fact that it was generally by a smaller amount, that two exceptionally small parents would tend to have a below average but not exceptionally small child. Two exceptionally large adults would tend to have a larger than average child, but not as exceptionally large as them. That the size of the exceptionality decreased, that it was falling back, regressing back towards the mean. So this was the argument made that the deviations away from the average regressed, they fell back slowly towards the mean. And so this perhaps slightly odd term has stuck for this explaining of some predictors, of some responses, based on some predictors. If somebody says a regression, what most people picture visually is a simple visualization of a simple linear regression. And we'll do this with one predictor variable and one response variable. So this is an incredibly scientific data set which has been totally made up. There's no real measurements here, it's just a load of dots on the page. But let's say we can have these as the x's plotted horizontally and the y corresponding y's vertically. If you were asked to sort of draw a straight line, trend line through that, I think most people would see where that's going. Larger x's associated with larger y's. And it would look something like that visually. Now that line, that dotted black line which is there, is placed there because I sort of looked at the picture and went, I think that looks okay. Looking again, maybe I've drawn it a little bit high in the top right. I don't know. But that's just how I visually thought the line roughly went. Now that's possibly useful for the point of predicting other values, but it also isn't very scientific or statistical. To define this a little bit more mathematically, let's say that we have a predictor x and a response y. If I measure x at n different points, I measure it at x equals x1, x equals x2, dot, 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 up to xn. And when x equals x1, I observe the response y was equal to y1. When we measure x equals x2, we observe that y was equal to y2. So the indices match, that the observation when x was measured at the value xn, the response y was measured with the value yn. A simple linear regression model is just this yi is alpha plus beta times xi plus epsilon I, where alpha and beta are constants. So in other words, what we have is this beta term multiplies the predictor. So if beta is positive, larger xi's will lead to larger yi's. And if beta is negative, smaller xi's will lead to larger xi's. And each term also has this constant alpha added to it. We'll often say that the beta is a slope coefficient, because if I plot this on the graph, the beta controls how strong the relationship between the x and the y is, how steep or shallow the line is, the slope. And the alpha term is an intercept, because that's just lifts the line up or pushes it down. And it's where it would intercept the y-axis, i.e. when the x is 0. The other term to note here is the residual term, the residual error term, which just says that if I suppose, believed the straight line, alpha plus beta times the x, what's the difference between what that simple straight line model would say and what I actually observed, which would be yi. So epsilon I is just the difference between the observation yi and what this model would say, which is alpha plus beta xi. The idea of the residual error is, I think, quite intuitive, but it's also easy to make a subtle mistake with this. The residuals are the distances between the fitted line and the observations measured in the direction of the response variable. And by that I mean we're not just looking at the distance to the line horizontally, because that's in the dimension of the predictor variable. I don't think many people think of that as the residual, but the one which many people do get wrong is just measuring the shortest distance to the line. So measuring at right angles to the fitted line, but that's not the residual either. The residual is measured in the y direction, in the response direction. So the red arrows, as drawn here, the ones that go straight up and down between the line and the point, are our residuals. So to fit a model, what we want is we want to select the best prediction line, such that the residual errors are not too large. It's easy to see that if I draw the line a long way from the points, my residuals will be huge. If I draw the line close to going through or near most of the points, I'll have a better model and smaller residual errors. What we'll tend to do is we'll tend to start by wanting a model such that the expected size of these residual errors is 0, and I'll be honest, I've skipped a bit of detail here. For the model that has a constant, a non-zero intercept term, this does mean that the sum of the residual errors is 0. So we'll have some positive errors and we'll have some negative errors, but that the sum of those should be 0 for the best model. And we'll explore that more in the next videos.